Hello friends, today we are going to discuss the quantum mechanics and the use of Dirac notations and photon polarization. So I will be explaining the photon polarization by taking into consideration the Dirac notations. So first of all, before we proceed, the first thing that hits our mind is why we need these notations. Like, they are very bizarre, and the only answer to this is that these notations, they actually work. So that means when we explain some phenomena using these notations, they actually define or actually verify the experimental results. That's why we use Dirac notations. So there is a method, or there is a thing which we use in this, and that is represented as a ket vector. That is represented as ket. So this is a ket vector which is being discovered by or represented by P.M. Dirac, the scientist who invented these notations. So that this is in the form of matrix. So first of all, I will be dealing with the mathematics of the Dirac notations. Then I will apply and I will try to explain the physical significance of these notations. So a ket vector is in the form of a matrix. And that matrix is in the form of a column matrix. It has a number of elements starting from A1, A2, A3 up to so on. And its adjacent matrix, that is known as a bra matrix, is represented by this. Oh sorry, you can mention it by A. And how we define that? That matrix is a matrix in the form of the rows, and it contains the elements which are complex conjugate of these elements. So this is how we find the bra matrix relevant to the ket. So these are named as bra and ket by the Dirac from the thing like bracket. That's how he named these things, ket and bra. So they are in the form of matrix, and it can be like any matrix in the form. This is in the form of the column matrix, and this is in the form of a row matrix. So that's how we use these matrices, and I'll try to explain how we use these matrices in physics. And for that, I have to discuss a few mathematical calculations related to the matrix formulation. So what happens? So the thing here is the ket matrix is represented in the form of a column matrix. That's what I want you to remember, and we will discuss how we apply or how we do various calculations using this matrix form. So ket is an eigenvector here. Ket is a matrix here. So what happens when I add two kets? Like this. So what it will be? A1, A2. I'm taking three elements here only for the simply, like this one. So how these matrices add? A1 will be adding here A1 plus B1, A2 plus B2, A3 plus B3. And what it is? So this is again a ket. So addition of the two ket vectors, it gives us another ket vector, right? When I multiply this with some constant like this, alpha is any constant, how are we multiplying alpha? A1, A2, A3. how it comes out, it is alpha A1, alpha A2, alpha A3. So this is again another cat. So the multiplying this with the constant, that gives you this one. So another cat. So alpha A is another cat. So one thing I forgot to tell you, that these A1, A2, they can be complex numbers as well, because I have mentioned that this bracket is having the elements which are complex conjugate of this, and you are quite aware what are complex number. Complex number can be written as in the form of x plus eta y, where eta is an imaginary number -1, and its complex conjugate that can be represented by x minus eta y. So that's how we represent a complex number, and if these elements are in the form of complex numbers, so you can find the corresponding cat and bra matrices by changing the row into the column and taking the complex conjugate of each of these matrices. So that's how we represent the cat and the bra notations in this matrix. So now a third term which is very important here, although these are also very important, the third term which has a very beautiful significance in physics, that we are going to discuss, and how we calculate that term, that I will be explaining here. So the two matrices, for example A and B cat, so this term is represented as inner product of the two cats A and B. So the two vectors, you can say, here A bra is multiplied with cat A, and how we solve this thing, this is the inner product of two vectors. It's equivalent to inner product, it's equivalent to the scalar product of two vectors that we call as inner product of cat A and B. So that is how we calculate that. I will be taking the complex conjugate of this matrix, and I will multiply with B1, B2 and B3. So that's how we do that. So this is a bra matrix. I will be writing it like this, and I'll take the complex conjugate of the elements and I will multiply it with B1, B2, B3. So how I solve that? I will be solving it A1 star B1 plus A2 star B2 plus A3 star B3. So that's the way, that's how I do that. Now similarly, I can find B inner product A. How I will be doing that? I will be writing the elements of B as like this, right? And then cat A will be written as this. So when I will be solving this, this will be B1 star A1, B2 star A2, B3 star A3. So this is how we solve that. So remember, when I am finding the inner product of B with A, I will write the elements of the B as this, like this is a bra vector, bra state, and this is a cat state, and this is how to solve that, right? So how, now here what I will do, I will take the complex conjugate of this inner product, right? So when I will take the complex conjugate of this inner product, it will be becoming B1 A1 star plus B2 A2 star plus B3 A3 star. Now you see here, this product is similar to this product. So you can mention here that A inner product B is equal to B inner product A. That's an identity which we have to remember for the future use. So that's how we solve these notations here, these properties here, right? So coming into the matrix form, I will define a matrix. For example, I'll take a general matrix M, and I have the elements of M matrix like this: M11, M12, M21, M22, M23, M31, M32, M33. So this is a general 3 by 3 matrix I'm taking here. So these numbers can be real as well as they can be complex as well. So what I do, I take the transpose of this matrix. How I take the transpose? I change the rows into the columns. So the element M11 will come here, then followed by M12, M13, then I'll take M21, M22, M23, then comes M31, M32, M33. This is another matrix. So when I write this matrix M transpose, I'll take the conjugate of this matrix. What I will be getting M11 conjugate. So I will take the complex conjugate of each element here. So you see, I'm taking the complex conjugate of each element. So this is a transpose conjugate of a matrix. We represent it as M dagger as well. M dagger is a transpose conjugate of a matrix. So when we do these operations, I'm taking the transpose and I'm then taking the complex conjugate of this matrix. I get the M dagger matrix. If M dagger becomes equal to M, like when I do these two operations, I'm getting back the same matrix, then that matrix is known as a Hermitian matrix. I'm still dealing with the mathematical concept. I have not come to the physics right now. These are the few basic concepts which you need to know, that this M dagger becomes equal to, then that is known as a Hermitian matrix. So I'll take an example here. I have a matrix, for example, M is equal to 1 plus iota, 1, no, you can say 1 here, 1 plus iota, 1 minus iota, and 3. This is a 2 by 2 matrix, so I'm just giving it an example. What I do, I take the transpose of a matrix. What will be the transpose? I'll change the rows into column 1. So this element will come here, 1 plus iota. This 1 minus iota will go here, and 3 will be down here, right? Now I'm taking the transpose of this matrix, so the complex conjugate of this matrix. 1 is a real number, it will remain as such. So 1 plus iota will be changed to 1 minus iota, it's complex conjugate. 1 minus iota will be 1 plus iota, and 3 will remain as such as it's a real number. So you see here, this matrix is again this. So in this case, M dagger, because this is M dagger is equal to M here. So this M is called or is known as Hermitian matrix. So there is some specific significance of this matrix when we do. There are a few more matrices, like you can see identity matrix we call. It's 1, 0, 0. The diagonal elements, the main diagonal elements are unitary, right? That is known as identity matrix. Another matrix that is known as unitary matrix, U. If U into U dagger is equal to identity matrix, then U is known as unitary, not identity, unitary matrix. So when the two matrices, their multiplication, and its multiplication with its transpose conjugate or dagger is identity matrix, then we call that matrix as a unitary matrix. Similarly, you can find the determinant of any matrix by multiplying. For example, there is a matrix A. I have its element A, B, C, D. Determinant of A you can find by using AD minus BC, like this. So the trace will be A plus D. Trace of A is A plus D. So these are the few mathematical calculations which we will be using in the further. So this is how we use this, like we find the Hermitian matrix, we find transpose and conjugate of a matrix. So this is all about the mathematics. So why I'm discussing the Hermitian matrix here, because this matrix plays a significant role in physics calculations. It has a very important role to play. So that I will be discussing with you right now, that what is the use of the Hermitian matrix in physics. So there is one basic property of the Hermitian matrix. So now what's the use of what's the basic property of the Hermitian matrix? That I will explain. So here, the basic property of Hermitian matrix is that when a Hermitian matrix is multiplied with the ket vector, so this is H, what I get a real number multiplied with a ket vector, right? This is the property of the Hermitian matrix. So Hermitian matrix, when is operated on this vector, so this equation is specifically of importance in quantum mechanics. This equation is useful when we apply or when we use the Dirac, ket and bra notations. So when this happens, when a Hermitian matrix is like applied on a vector and we get this, so then this vector, that is known as eigenvector, and this is known as eigenvalue, and obviously this H is known as a Hermitian matrix. So there is a certain matrix, 2 by 2 matrix can be used. There are specific elements which comprise to form a Hermitian matrix. Not every matrix is a Hermitian matrix, right? So this lambda n, you can say it's an eigenvalue, right? So this is the significance. Now what this mathematical term represent in physics, right? So in physics here, this H represents an operator, right, or any measurable, you can say. This A in physics, it represents a state, a physical state the system is in. And this lambda, it represents the actual value or the observed value of the physical quantity. So that is the physical significance of this equation when we use, right? So this eigenvalue lambda will represent the actual value of the measurable, ket A, that represents the physical state of the system, and H is any operator or it's any measurable. That is the meaning of this equation in physics that we will be using. So I will be explaining certain phenomena using this equation. So as I told earlier, we will be discussing the polarization of the photons. That I will be explaining the polarization of photons by using the Dirac's, ket and bra notations. Okay, so here I'll take the example. That I am using unpolarized light and I am passing that unpolarized light from a polarizer. We'll explain that the result obtained experimentally, they can be demonstrated by using the Dirac, ket notations. I have an unpolarized light. I'm passing it through a Y polarizer or vertical polarizer. What I will be getting, I'll be getting a polarized light, polarized in Y direction, right? So when I will passing this polarized light through a vertical polarizer again, there are 100% chances of getting the output, right? So this is, in second case, what I'm doing here, I'm passing an unpolarized light from a Y polarizer. I'll be getting the output here, and I'll pass it from the horizontal polarizer. I will get no output, right? In third case, I'm using the same formula like this. I'm passing it, I'm getting the output in the Y direction. I'm passing it through a polarizer which is placed at an angle 45 degree. What I will be getting, I will get 50% output, right? These three things which I have mentioned here, they are experimentally proven, they are experimentally verified. There is nothing unofficial about it. They are experimentally verified. So in generally when we talk about the classical concepts, generally, if I am passing this polarized light through a polarizer which is placed at angle theta with this vertical axis, I'll be getting the output which is proportional to cosine square theta. So this is experimentally proven. This data has been collected and it is being verified experimentally. So the thing here, our main motive is to explain this phenomena, and by using the cat and bra notations. So what is happening here? What I do? So this, you see, this is in cat and bra notation. I will write the horizontal and the vertical states of the polarizer, of the photon, by using X and Y cats. I beg your pardon. So this is a Y cat, sorry. So X will be 1 naught and Y cat will be 0 1. So this is how I represent the vertical and the horizontal states of the polarization of the photon, right? So these are the ket vectors which we have to remember and which we have to use. I'll explain why we use this 1 0 and 0 1 as the ket states, as the polarization states of the photon. So now I'll define a term in physics which we mentioned as the inner products of the two kets, that is X and Y. If you remember, X and Y, that is how we calculated that. I will write X as 1 0 here, right, and Y as 0 1. You see here I'm using these row elements corresponding to the X bra because it is a real matrix, there is no complex number. So it will, if it is a complex matrix, then I'll use the complex conjugates here, right? So how we solve that? I'm writing it as 1 multiplied by 0 is 0 plus 0 multiplied 0 0. So this is a very interesting term in physics. This we call the inner product of the two states, right? I'm going to explain it here. X, Y inner product. This is quite similar to the scalar product of the vectors. If I just want to point it out, this is quite similar to scalar product of the vectors, but in physics this is inner product that is defined as, if I prepare a polarizer in Y direction, if I prepare a polarizer in Y direction what are the chances of getting the output in the x direction? This is the physical significance of this term. I repeat again, if I prepare a polarizer in the y direction, what are the chances of getting the product, the output in the x direction? You see clearly here, I get this 0. So here, this xy, that is also referred as probability amplitude. That is also referred as probability amplitude. And consequently, the term xy square, that is known as the probability of getting the output. So if you see here, if you multiply this, if you find the square of this term, you will get 0. So there is no probability of getting the output here. That's quite obvious, right? So that's been experimentally proven as well. So this is how this term is. Now the very interesting thing is, very important thing I want to mention, why this term represents the probability. There is no there is no theorem, there is nothing. Why it is known as probability? Because it satisfies the experimental results. That's why we call it the probability of finding the output. So this is how so you got the significance of this inner product in physics. Now I'll explain all the data, all the experimental observations by using this Katz and Bra notation. Right? Now I'm coming towards when I'm using y inner product y. So what it means the probability when I prepare the polarizer in y direction, what are the chances of getting output in y direction? So how I'm going to find it? I write it here 0, 1, sorry. Now we have to find complex like conjugate row matrix, then 0, 1. Right? So this is the y Bra matrix and this is Ket matrix. How I'll write it is 0 plus 1 is 1. I'll square it here. I have to find the probability. Probability is again 1 square is 1. So that means there is 100% output that I will be getting. Right? So probability becomes 1. So similar is the case when I solve using x. You see what is x here? 1, 0, 1, 0. You find it 1 plus 0, it is again 1. So the probability of the output is 1. No, very important thing I forgot to tell you. When the matrix has the complex numbers, this product is y, x, x, y. So ultimately it is xy conjugate and xy conjugate. You see, you have a matrix for, you have a complex number z is equal to x plus iota y, right? How you write z modulus is z modulus square, it is z into z conjugate, right? So that's how I am representing if it contains the complex numbers. Since I have only the real numbers, so that's why I mentioned the term like squaring this term. So this is the thing you have to remember. So when I will be when we'll be discussing the spin states of the electrons by using these Dirac notations, we'll be coming to this point because that contain the complex numbers and the Hermitian matrix contain the complex number of this. So this is how we can explain this. Now, when I have a case when polarizer, now the polarizer is placed at an angle 45 degrees, I represent that state as a forward slash, or you can say like this, right? This, right? So I have to find the probability of getting the output when the polarizer is placed at an angle 45 degrees or some axis. So this angle represents the 45 degrees axis. So I will mention that it is a linear combination of the two states, x and y, like this. It's a linear combination of two x and y, right? So what is x here? X is 1, 0, and what is y? Y is 0, 1. So when I add this term, it becomes 1, 1. Now let's find the probability of getting the output. How I'm going to find it? I have to find it becomes, sorry, so this becomes this. Now what I have to do, I have to find out the inner product. So this state, if you remember, so I represent this state like this. I'm sorry. So this is, now what is the inner product of this? Inner product is like this, right? How I'm going to find out the inner product? I will write the first elements like this, then so this is how we find the inner product. Now what? This multiplied by this 1, this multiplied by this 1, 1 plus 1 is 2. So what is the probability? What is the probability of getting the output here? It is 2 square. So it is 4. So that means there are 400% chances of getting the output, which is not true. So we have to make changes here. I have to change. I have to write down the state in such a manner when I will get the output, there will be 100% chances, because I am preparing the polarizer in this state and passing it through the polarizer which is along the same axis. So what I will do, I will multiply this state by 1 over root 2 like this. I'm sorry to mention that don't forget to change, this is a cat vector here, right? Yeah, a cat vector. Just messed up here. Sorry about that. So this is how we do, right? So the corresponding vector will be 1 over root 2, 1 over root 2. This is the forward slash vector, this is the cat state. This is the state, physical state of the light which is being polarized at an angle 45 degree with the x-axis here. And similarly you can find out the backward slash here. That will be 1 over root 2 minus 1 over root 2. This is how we represent these states, right? So now if I apply these notations, right, I am finding that what are the chances of getting the output when the light is prepared along x-axis. What are the chances of getting the output when the polarizer is placed at an angle 45 degree, right? And what are the chances of getting the output through x-axis? How are we going to find it? I write it 1, 0 for the x, and for this is 1 over root 2, 1 over root 2. When you solve that, it's 1 upon root 2 plus 0, you get 1 over root 2, right? So now what is the probability of getting the output? I'll square that term, you will get 1 upon 2, that is 50% chances of getting the output. This is being explained by this. So this is how we use the Dirac cat and bra notations by using this is how we use the Dirac cat and bra notations to explain the photon polarization, right? So that's all for today. So in next session we will be discussing how we define the spin states by using Dirac's notation.